Okay, so this is the first recording in the last chapter, even though it is chapter 4.9 called the antiderivative. I am going to cover this with the chapter 5 material. So, what is the difference between an antiderivative and an integral? Well, an antiderivative has what we call an initial boundary condition, IBC, where you are looking for the exact solution to the differential equation. Now, what I mean by a differential equation is that we have something that is the derivative of another function, but we need to find the exact solution, which means finding the value or the values of C, because there could be more than one C. In the book, they use subscripts to differentiate them. C sub 1, C sub 2, and so on and so forth. So instead of just finding a general solution, we start off at the end of chapter 4 finding an exact solution. So in this example, I'm given a derivative. It's a differential equation, 4x plus 6 plus the sine of x, with the initial boundary condition that f of 0 is equal to 4. Okay, so I'm going to integrate this, which means, of course, that you need to know your integration formulas. Okay, so I'm going to integrate this. And that's going to give me f of x, the original function, is equal to 4x squared over 2. So again, you need to know your rules here, plus 6x. And the integral of the sine is minus cosine. So this is minus cosine of x plus c sub 1. I'm using c sub 1 even though I don't have to, because we're only finding one integral with this example. All right, I'm going to simplify this in a second, but I want to show this to you. This is the raw integral. Now, it's still a general solution because we haven't used the initial boundary conditions yet, but we will in a second. So let me simplify this. And I get f of x I get f of x is equal to 2x squared plus 6x minus the cosine of x plus c1. Now I'm told in all of these problems in 4.9, you'll be given an initial boundary condition. I'll just call it the IBC, that f of 0 is equal to 4. So I'm going to plug in 4 for f of x, and I'm going to plug in x equals 0. All right, so I'm plugging in x equals 0. And for f of x, I'm plugging in 4 because that's what you're being given in the problem. Okay. Now all I have to do is solve for C1, C sub 1. All right, so I've got 0 plus 0 minus 1. So I've got 4 is equal to 0 plus 0 minus 1 plus c sub 1. So that means that C sub 1 is actually equal to 5 if I add 1 to both sides to solve for C sub 1. That means that my particular solution now is f of x is equal to 2x squared plus 6x minus the cosine of x plus 5. So that's the antiderivative right there. And again, notice that that is a specific solution, and it does fulfill the initial boundary condition that f of 0 is equal to 4. If you plug in x equals 0, you get 4. Okay, that's one example. All right. I'm going to pause this and try a second example, although the honor room I need might be a little bit more than what I have on this handheld board. Okay, pausing. Okay. Second example. Here we have a second derivative, f double prime of x. And in this case, f double prime of x is equal to negative 6e to the x plus 4 sine x plus 8, with two initial boundary conditions that f of 0 is equal to 4 and f prime of 0 is equal to negative 10. What does this mean for us? Okay, comparing this with the first example where I only had to integrate once, I have to integrate this twice. All right, so integrate it once. Integrate it once. And I get f prime of x is equal to negative 6e to the x. Again, you have to know your integration formulas, have them in front of you. Minus 4 cosine x plus 8x plus c sub 1. All right, so that's the first one. Now I'm going to have to integrate this to get all the way back to f of x. Okay, so integral of f double prime gives me f prime. And when I integrate f prime, then I get f of x. So one more time. Remember, we're trying to find the specific solution to this. So integrate again. And that gives me f of x is equal to negative 6e to the x. And the integral of the cosine is a sine, so I got minus 4 sine x plus 8x squared over 2, which is plus 4x squared, plus c1x plus c sub 2. So now I have two constants of integration here. All right, and I'm using subscripts to separate the two c's. C sub 1 is different than C sub 2. Usually is, it doesn't have to be, but I guess it usually is. Right, now I can start using my initial boundary conditions, and I'm going to start with f prime of 0 equals negative 10. All right, so that gives me negative 10 is equal to minus 6 minus 6 I'm letting x equal to 0. That's minus 0. No, it's minus 4 plus 0 plus C1. So that means that C1 is actually equal to 0. Okay. So I'm letting x be equal to 0 in the first derivative, and I get C1 is equal to 0. And yes, of course, C1, it's very possible that C1 is in fact 0, as by this example. Now, one more time. Now I go back to the original function f of x. Now I already know that C1 is 0, so that means that I have f of x is equal to negative 6 e to the x minus 4 sine x plus 4x squared plus C2. And I know that f of 0 is equal to 4. So plug in 4. And again, I have minus 6 minus 0, because the sign of 0 is 0, plus 0, and C1 is 0. So that's 0 plus C2. So adding 6 to both sides, I get C2 is equal to 10. That means that my exact solution, f of x, is equal to minus 6 e to the x minus 4 sine x plus 4x squared plus 10. And that's because C1 is equal to 0 and C2 is equal to 10. So here's my exact solution all the way down bottom here. And notice that that satisfies the initial boundary conditions given in the problem. All right, so yeah, they're covering these exact solutions first. They're called antiderivatives, which is going to be different than finding the general integrals that we're going to get into in chapter 5. Chapter 5 is sort of a short chapter, but it is a quantum leap. And of course, it's the last chapter that we're covering in this Calculus 1 class, so it's important. This is the quantum leap that goes from differential calculus to integral calculus. All right, folks, that's it.